Okay, welcome back to Advanced Algorithms. Last time we did an excursion to a singularity analysis of generating functions, which was, for many of you, maybe a bit far away from the math that you're used to, because it involved a lot of complex analysis. The intention was not to scare you away from this topic, but to give you some in-depth summary of what's possible with that. But I guess the overall idea might have been lost a bit in the computations. So let's briefly summarize again what we've seen before we continue. So this will be just a very high-level overview. The key idea was that we had some sequence of numbers. In that case, it was the size of our search space for this, it was directly the running time of the algorithms for with or without interleaving. So that was this Tn. And that's world A, so to say. That's a world where you're at home. You know how to set up recurrence equations for such sequences that they fulfill or that characterize such sequences. And in some lucky cases, we can just guess and verify exact solutions. For some others, there's things like master theorems, by which I mean theorems that give you a simple, broad, rough idea what the solution looks like. But then if these two are not applicable, then it's often not so clear what to do next and how to proceed. And one way to get a bit further is to change to the world of generating functions. World B, so to say. And there we're dealing with functions of this kind, power series, where you have the number sequence as coefficients of the powers, so that the whole sequence is captured into one single function. Well, and if you're lucky, then you can represent such a generating function by a concise term that does not explicitly list all these individual coefficients. So, I mean, I haven't even given a simple example, but you know maybe that this function corresponds to the sequence of all ones. And many more examples exist where there's a simple representation for the generating function, a closed form. And in some others, there's at least something close to that. But, okay, I needed a bit more space here than anticipated. The equivalent of the recurrence equation is a functional equation, which means nothing more than an equation involving t. And for certain kinds of recurrences, it just happens to be that this equation is actually easy to solve. In our case, it was some polynomial. It was essentially just a linear equation in terms of t. It involved factors in front of t that were polynomials in z, but that's a different regime. So the solution for t was elementary in our case. And you can even deal with cases where this is more complicated, but we won't do that. So in our case, we found an exact solution for this function. At least under the assumption that we have a closed form generating function for this tall sequence fn. But still, this is more than we had in the world of sequences. Even in that case where we relied on the existence of another generating function, it still brought us a step further. But there's also sequences where we can have doubt that there's even an exact solution in some elementary form, where you can give hints that there's simply no nice solution for this recurrence whatsoever. It's defined by some numbers, but there's no single nice term that captures these sequences. But it might still be even if it seems like this is not possible to get, we might be happy with an asymptotic approximation of the sequence. Because at least for algorithms, we are used to dealing with only asymptotic approximations of running time. That's part of our core business, this abstraction. It's a debatable one, actually, right? But a well-accepted one. So often we are happy with that. And we've seen, that was the core part of last time, that sometimes we don't get an exact solution for this equation for T of C. But even if we might simplify, we might make our life much simpler by approximating the function. Now here we approximated around n equals infinity. So it's in a formal sense, it's some limiting process, and we approximate in the proximity of this limit. And we can do a similar thing here for the functions. We've seen that there's so-called singular expansions, which was expand T of C around such a pole. So we had some part of the function, and then an O of this specific form, 1 minus C to the alpha, for example. And then the cool part was this transfer theorem that finally allows you to go back to world A, to the sequences from the generating function. And the merit of all this hassle with complex analysis and so on is that you can introduce approximations early on in your computations. So if you remember or scroll back to the solution of the homogeneous equation where we found the exact solution, the final result was also in the form that there is some linear combination of terms of this form, a power, an exponential, and a polynomial part, and so on. And the proof essentially showed the exact solution in terms of this generic form, but it was a bit of inconvenient that we had to carry around all these terms, just to note that in the end only a single one is actually the leading term, and all others are much smaller because they are exponentially smaller if they come from different roots. And the new methodology that I introduced to you last time allows you to approximate T early on so that you only retain the dominant part of T and then translate back how much of an error term this approximation gives you. And well, I'm aware of the fact that it was a very concise introduction to this topic, skipping a lot of the mathematical backgrounds, which is unfortunately not part of the usual curriculum in computer science. Well, it's not so much that you have to learn. Many of the tools you can just apply these days as black boxes, even if you're not willing to make an effort and understand them. In terms of the application, so for the interleaving business, this meant that interleaving gets rid. So this was what we showed, right? The running time with interleaving was in O of the running time, or in O of the search space size for the homogeneous equation, which was essentially like skipping the amount that the time that you need in the branching step. Without interleaving, that step translated into a factor in front of this alpha to the n, or alpha to the k. So interleaving gets rid of this factor. So it was r of q of k. That was from the kernalization in the beginning, and r was the branching complexity. And that was a factor in front of the alpha to the k in the original algorithm. And with interleaving, that one is just gone. And the only thing that we needed for that with this more advanced machinery is that this r is less exponential than alpha. So there's a strictly smaller basis. We even assumed in the beginning that r is actually a polynomial because in all the applications you wouldn't like your branching to be too expensive. But still, mathematically speaking, it makes sense to extend that a bit, and the result is still the same. So that was just to finish that discussion. And here's a bit more of advertisement. You can extend the analysis that I've showed you using the singularity analysis issues. You can extend this to further recurrences, and simple thing is to add constants in front of the recursive calls, so you don't have one recursive call but a certain number of the same type. That essentially only changes the characteristic polynomial, and the rest remains the same. Then you can consider completely different kinds of recurrences. That leads too far to go into details, but as long as you can show some singular expansion of the generating function, the same machinery applies to get back from world B to world A. That's at least good news. And well, one example for a recurrence that also allows to solve for the generating function is one like the quicksort recurrence. So you might remember that from a basic algorithms course. It looks a bit different, and it's a bit different to solve, but it's also one where this is possible. I've briefly re-derived this formula for the case that alpha is a negative integer, no, positive integer in that representation. You can extend this to any real alpha as long as it's not a negative integer, because then these would be just polynomials, and then they only have a finite number of non-zero coefficients. That's the only way, the only reason why this is excluded. Okay, and if you want to learn more about that, there's a large book and a good online course on analytic combinatorics. Now, there's a final thing to discuss on interleaving. We've seen that interleaving improves the running time, but that was based on a worst case analysis, which might have been very pessimistic. Maybe that's not even possible that this happens as the actual running time. Okay, that is not perfectly clear because we always showed upper bounds in the analysis. But there's a simple example where, at least in this specific case, interleaving does help. We'll look again once more at the vertex cover instance and at a very specific family of graphs. So let me first draw these. These are on the cover of the printed lecture notes, so you might recognize this picture. So we have a long tail, how they call it in the original version. So these are a certain number of, it's just one long path. And then there's a structure called the head that consists of this flower-like structure. So in total, k minus 2 for these. And then we have a certain number of copies here of these little structures. So these arms are all the same. And then we have k minus 2 here again. So we call this part here the head. And this long part is the tail. Now it's a generic family of graphs with a parameter k. I think we start at 2. Then we let the tail have 3 times k plus 1 vertices, just one long path. Well, in the head, as given, we subtract 2, and then we have one node that has k minus 2 neighbors, each of which has k minus 2 leaves dangling on these. Okay, you can convince yourself with a little diligence that the smallest vertex cover for this graph with parameter k has 5 over 2k minus 3 over 2 vertices. Which is essentially to take these here, and then every other node in the tail, which is what you have to do. Maybe so this should be, okay, now it's not even clear if it's odd or even. Okay, maybe this ends like this, I don't know. So this is just an, by counting properly, you find that this is the size of the vertex cover that you need. And the input for vertex cover now is G with the same K. So this is a good deal larger than K. That means all these graphs, all these instances are actually no instances. Is the setting clear? So we're considering this family of graphs, and the same K is also the threshold that we use. The number of vertices in the graph is the next thing that we need. So let's call it n, the number of vertices. That's for the head. We have the k minus 2 flowery structures. Each has size k minus 1, k minus 2 leaves, and the red node itself, plus the one in the middle. So plus the tail. And hopefully if you multiply out, that should be k squared plus 4. So with these preparations set up, we now compare an algorithm, the simple algorithm actually, with a 2 to the k search space. So the simple algorithm that branches over the endpoints of a single edge each time. We compare this algorithm and combine it with the simplest kernelization that we had, namely the k squared kernelization called Buss's reduction. So algorithm A uses this reduction, which was to just remove all high degree vertices, because every node with a degree greater than k must be in the vertex cover if the vertex cover should have size k at most. Remember? And then afterwards, after the kernelization step, you can already think about how much it helps in this graph. you do this, I called it simple FPT vertex cover. That was branch over the edges. Well, and to make things simple, we assume that these k edges in the algorithm were just picked non-deterministically. So you say there's some k edges, oh, not non-deterministically, but just arbitrarily. And we pick the edges from right to left. So we start with the tail. This is somehow cooked up to make the example go bad. But it's possible, and it's a worst case analysis. So that's algorithm A. Algorithm B is the same, but interleaved. So whenever we did a step of branching, we reapply this reduction. Now let's see what happens. Well, the reduction certainly does just nothing because there's no node with degree higher than k. So it doesn't change the graph. And here, picking vertices from right to left is pretty unfortunate because we will have to branch for every of these edges that we take. Maybe we don't start with this. Well, okay, the simple algorithm doesn't even remove degree 1 vertices. So it starts here, and there's enough nodes so that you can just spend all the 2 to the k steps in the tail. And after that time, you will notice that there's a good deal of the head left with edges that you will not cover. So the kernel is just gkk itself. It's not changed. And the second part needs the full 2 to the k search space. And then it finds that there's edges left, so it's a no instance. So if we're generous, it takes some omega of 2 to the k time. We should probably add a not so much, if I recall the algorithm. It was sometimes some linear thing in the graph, right? So this should be essentially it, and the kernalization is of course dominated. Now with interleaving, we also start with the kernalization that doesn't do anything. And let's assume the same unlucky ordering of the edges. But once you reduce, you remove 2 edges. So first kernel is the same. Then we remove 2 edges and branch into 4 cases. But then we have reduced the parameter to k minus 2. Well, and at this point, there will be a part of the tail will be gone, but all the head will still be there. But now with k minus 2, these nodes have degree. Okay, maybe we need one more, right? Maybe we need 3 edges because the reduction says degree is strictly greater k, or is it?
The central node, because it has.
Oh, it has. Yeah, you're right. Of course, it has the connection to the tail, so it has degree k minus 1. Yes. So center of head. So after this step, the center of the head is deleted. And then the remaining ones here, they have then k minus. Okay, they are removed in.
They also have k minus.
They have the same degree, and we remove them in the same step at one at one shot. So yeah, so it's even simpler. That means the complete head is deleted. Well, the isolated nodes are still there, but they are harmless because they're never chosen as edges. But since we have to pick all these nodes we delete, we have already used up all the nodes that we can afford for the vertex cover. So this will immediately give us a no instance then. Since there's some edges in the tail left that we can't cover. So strictly speaking, the running time is not even exponential in anything. It stops after a constant number of branching steps. So it's just given by some polynomial in the size of the graph. So this is an extreme case because the input graph was very tailor-made to help this reduction. But it still shows that interleaving sometimes helps a lot, and that it's not only an artifact of the analysis that we did before. In practice, it might be a trade-off because running the reduction all the time adds a certain constant factor to the running time. Remember that we've shown for the running time functions that the new one for interleaving is in O of the search space, but O still leaves room for a large constant potentially. So I think in practice this only helps unless this kernalization is very sophisticated. If you remember the one that we've seen for vertex cover that solves an LP each time, it might be doubtable whether this is giving you a speed up. But I might add that for the specific LP that we discussed, you can actually solve it by a combinatorial algorithm that even avoids the rounding issues. Maybe I'll cook up a nice exercise out of this if it doesn't explode too much. And then it's probably helpful even in the reduction for vertex cover. Okay. That completes the discussion of interleaving. There's a last topic that's a bit more technical again, but I will skip a few details for that reason, because we've already spent a lot of time in proving negative results. But we've seen now a few algorithms, FPT algorithms for certain problems with a certain exponential part. And for the vertex cover problem, we've even seen a few of them, and we saw that we could improve the basis of the exponential growth. And the question is, how far can we go with that? And the same question could be asked for the closest string algorithm that we've seen last time with this humongous k to the k factor. I already hinted at the result that this is essentially best possible. And I want to quickly show what precisely I mean with that statement and give you the machinery to apply that to new problems. I should add, this is a relatively new topic in this FPT field, and maybe there's also new results to be shown that use nicer machinery or more elegant theory. So I'll here just confine myself to the basic part. So there's more behind this section title that I will show, but the basic idea of the type of results should be clear after this session. Okay, ETH is not Eidgenössische Technische Hochschule, it's exponential-time hypothesis. This is a relatively old, well, it's from 1999. Is that old or not? Depends on, well, it's newer, younger than the P-NP question, which is from the 70s, but there's also newer stuff in complexity theory. So it's the following hypothesis. It's concerned with the 3-SAT problem. And I wrote it here in terms of the parameterized problem where the parameter is the number of variables. I added it explicitly because this will be important. And this conjecture says that there is some constant so that we need 2 to the epsilon, this constant, times k time for solving 3-SAT. So this together, 2 to the epsilon is just some number, right? So that is some c to the k. And since epsilon is greater than 0, this will be larger than 1. So it will be some 1 plus delta to the k, which is maybe more intuitive. So it says there is a delta greater 0 so that this holds. That's the first alternative formulation that I gave here. But it doesn't tell you what this epsilon is. And, well, in a sense, we don't know. So this is the first bad news. You can make stronger assumptions that also try to get hold of this constant, but they are not so widely believed and not so well supported by other things. So like many times in complexity theory, this hypothesis, this one is indeed widely believed, but of course we don't have a proof. It's maybe trivial that if ETH is fulfilled, then we have proof that P is not NP, because 3-SAT is a NP complete problem. And if this is, no, sorry, it's the other way around. If P is not NP, then wait. It's a more specific statement than P is not NP. So if this fails, it doesn't tell you that P is NP, because it still doesn't give you a polynomial time, but just a sub-exponential time algorithm for SAT, which is not enough to prove P is NP, which means the other way around. That if we can prove that P is not NP, well, if we prove that P is NP, then this also fails. That's maybe all I can say. Yeah. People have looked at 3-SAT a lot and, like for Vertex cover, improved the basis of the constant from the trivial 2 to the k, which would be just try all different possibilities, to some 1.3 something to the k. But not anything further. And therefore, the hypothesis is widely believed. Sometimes it's simply stated as there's no sub-exponential time algorithm. And I will write it in the title sometimes like this. But you should be a bit careful because sub-exponential is not well defined. This is a specific notion of sub-exponential, namely for every epsilon in O of this here. That's one definition for sub-exponential, but there are others and they're incompatible. So this is a bit taken with a grain of salt. The other formulation that you'll see sometimes is 2 to the small O of k. which is also not precisely the same, and maybe it's even unclear what exactly is formally meant by this, so I'll try to avoid this also. But this will mean that we will often have such a multiply quantified statement. For any epsilon there is an algorithm and so on and so forth. That doesn't make it nicer, but at least it's precisely clear what we mean by it. Okay, how we're going to use this is assume we want to discuss a problem x. If we can show that an algorithm for x that has some time that depends on a parameter k of x and the size of x, if such an algorithm implies an algorithm for 3-sat for all epsilon. So we want to have the same, this kind of running time, but for all epsilon. So we have to show a whole family of algorithms. That's just the negation of this, right? So ETH says there is an epsilon so that all algorithms are above this running time. If we can show for all epsilon there's an algorithm with at most that, then we can actually show there is no such epsilon. So that would mean we have, so this means that this hypothesis doesn't hold. And then unless we want to believe that, that means we don't have an algorithm for x with this running time. Is the idea clear? Okay, puzzled faces and some nods. It will probably be clearer if we substitute x for a real concrete problem. But there's one issue, as we will see in a second. We have to preserve this parameter k, which, as you should remember, is the number of variables in the formula. So let's revisit one famous reduction from 3-sat to one of our most famous problems, which is vertex cover. So how can we reduce 3-sat to vertex cover? If we are given a formula phi in 3-sat, and we assume that it's given as a set of sets of literals. We've used that representation before, so each of the L's is a variable, or the negation of a variable. And the reduction is based on the idea of gadgets. We need gadgets for variables. And we can, in the simplest case, say a variable is represented by this partial graph, which is just two nodes and an edge in between, and we will mean that a node that is contained in the vertex cover means that the literal given in its label is set to true. And every minimal vertex cover so any vertex cover will have to pick one of these two nodes to cover the edge, and minimal ones will usually just pick one of these two. And then we also have gadgets for clauses, and this is just a triangle of 3 literals. Okay, the order doesn't make a difference. And what remains is wires to connect the literals to the variable gadgets. And here we do exactly, if this is actually x1, then we connect it to this. If this is x2, we connect it to this, and so on. So we connect each of these literals to exactly one literal, to the corresponding literal in the variable gadgets. So we'll see that if phi has n clauses over k variables, then we will have the number of nodes will be 3n plus 2k. That's just how we drew it. Now the threshold for vertex cover we also have to compute. It's just so that we pick 2 vertices from each of these triangles and 1 from the variables, which means 2 times the number of clauses plus 1 times for the variables. And in fact, any vertex cover of this size has to pick exactly 1 of the vertices from each variable gadgets and 2 of the vertices from each clause gadget. Because this is so tight, we have to pick 2 of these and 1 from these. So it's clear that there's a 1-to-1 correspondence between any vertex covers of this size and a variable assignment, which we get by simply setting the variable so that the literal that's included into the vertex cover is set to true. And since we connect, so if this literal is set, then we don't have to cover that edge. That means we will take these 2 vertices into the vertex cover to cover the edges of the clause gadget. And this is exactly possible to have a vertex cover of this size if and only if we find a satisfying assignment for all the clauses. Because if we have to, if we don't find for some clause any of the variables that's also any of the literals of its literals that's covered in the vertex cover, then we would have to add this 3rd node, and that would give a larger number of nodes in the vertex cover in total. So this is fine. That gives us a nice reduction. The graph with this threshold, say k prime, is a yes instance if and only if phi is satisfiable. So this is the well-known poly-time reduction from 3-set to vertex cover. Now if we want to use this to show that there's no sub-exponential algorithm for vertex cover, the problem is that this threshold k prime here is essentially linear in n in the number of clauses in the formula, so in the size of the formula, and not only in the parameter in the number of variables. But the exponential time hypothesis only makes a statement about the number of variables. So it says there's probably no algorithm that's fast in terms of the number of variables, but the formula might be much larger than this. And to make use of this, even though our reduction here produces a much larger parameter, we will have to work a bit harder and see if we can strengthen the result given by the exponential time hypothesis. Now this is the technical part. We can actually transform any 3CNF formula into one where the number of clauses is linear in the number of variables, but we will have to live with an exponential blow-up in a different sense. So the precise statement is, if you fix any number epsilon, and well, as I said before, we will have to use all quantifications in all these statements because ETH is stated like this. So if you fix any epsilon, there is some constant which in the end will give you the number of clauses in the output. And for any such combination, we can compute for a 3NF formula that has n clauses and k variables, where we don't know how these two relate. We can compute an equivalent formula that is the disjunction of 3 C and F formulas. So that now we have an additional quantifier outside. But each of these psi I has the same k variables and at most k times k clauses. So this must be k in both instances. So each of these psi's is small in the sense that it only has a linear number of clauses. But we can have up to 2 to the epsilon times k many such identify such parts of the formula, and this is essentially needed to be equivalent. And hence also the computation to produce these formulas must of course be at least this, and it's essentially this. So the proof of this lemma is a technical nuisance playing around with set formulas. So this idea is not helpful without a sketch. If you have the 3 set clauses in phi, this is essentially a set of sets. We used that representation before. So let's just do a very small example. And assume that these clauses are overlapping. So then you can draw these sets as such. Well, this is not a set, that's confusing. Let's try it like this. Then the second clause is this. And the last one is not x1. Is this. Then this is a structure that has been called sunflower. And the petals are just here, the outside parts, and the heart is the part they have in common. Now to satisfy the original formula, it's clear that you either have to pick one of these variables or literals and set them to true, and then all are fulfilled, or you have to satisfy all petals. And therefore, they take this formula and branch into the two cases, either satisfy this, or that is satisfy all of the 3 outsides. But you have to do that in a careful order. I mean, how many of these petals you can find. A large formula will have many such sunflowers, but you have to reduce them in the right order. And then if you do all of that correctly, you will get a bound on the number of instances in the end that you produce. And the point is, in this example, if you consider the case where you branch on the petals, you have size 1 literals, size 1 clauses left. So these essentially force a certain assignment of the variables, and here you already see that this can't be satisfiable. So many of these branches will actually be smaller, but even if that doesn't happen too early on, you can still bound the number of clauses that you will have in the end. So we will use this as a black box to prove this theorem. This is again considering the p-sat problem, but this time we say that for every constant, again this all quantification, we have an algorithm that runs in this time. So any algorithm must run in 2 to the c n plus k, where now the number of clauses is also included. And this will be much more helpful. So for the proof, we assume that we will show that if such an algorithm exists, then we will find an algorithm that ETH says it does not exist. Therefore, we will show that it's not true, and then the converse gives us the statement. So we assume that for all C greater 0, we have an algorithm AC that solves 3-sat in time as given. Now for an algorithm, we will usually get some polynomial part also. But it's clear if I make this C here, this one a slight bit smaller than this one, then this polynomial part will be dominated by the exponential part. Now assume, so we use this algorithm to now construct a different one, a family of algorithms B delta. So for any given delta, we will describe what the algorithm looks like. And the goal is that this solves 3-sat in the stricter time, namely the one that we had in the ETH. So if we are able to show this, then we have shown that this doesn't hold, ETH fails, then the converse means that such an algorithm doesn't exist. Okay? So how does this B delta look like? Of course, it uses the sparsification lemma. The sparsification lemma said for every epsilon there is, and so on. So we set the epsilon from the sparsification lemma to delta half. And then we get some constant k. Right? For every epsilon we get a k, so that this bounds the number of clauses. So now comes the first step. I made a mistake. First, we transform the input formula into this sparsified instance. So with the one that we've just chosen. So that means that each of these, the number of clauses here is then k times k. And the next step is for each of these, each of the individual parts of this large disjunction, we use our algorithm AC, where we choose this constant C as delta divided by 2 times k plus 1. You will see in a second that this is just the constant that works out. There's nothing specific about that number otherwise. Well, and then, of course, you return yes So you say phi is satisfiable if and only if any of these is satisfiable. And by the sparsification lemma, these two are equivalent in the usual sense. So any satisfying assignment for these has to satisfy at least one psi I, and then phi is satisfied and vice versa. So it's clear that this algorithm is correct because it just uses this reduction. But the interesting part is the running time. So step 1 uses essentially the sparsification procedure, which we claimed there that has the following running time. I used the same b for all polynomial parts. Actually, you should use a different one each time, and in the end, you can take the largest one. But I'll just assume that we choose a large enough one right from the beginning. Sometimes people also use an O star that just suppresses all polynomial parts, but I haven't seen a formal definition of what this O star actually looks like. It's intuitively clear for any function of this shape what it's supposed to be, but I prefer this version, even though it's also not formally, it's not very correct to use the same b. Step 2 has to iterate over these many formulas, and again from the sparsification lemma. So this was the epsilon. Maybe I should write epsilon here first, and then we chose epsilon just to be delta half. Here we had so many psi's, and for each of these we use our AC, which had this running time. So with the C, you can just copy, and now we insert the definition, right? So it's epsilon k plus. If you insert this here, the n, I simply copied the n, but it's so what we have here is actually the size of these psi's, right? So they have the same number of variables as the original phi, but they have only these capital K times small k clauses. So let's write the size of the psi's, and this is just bounded by this. So we have inserting C from above gives us this. And then this is bounded by capital K times K plus another one, capital K plus 1 times K. And then these cancel out. And the epsilon, we can also directly insert here, is delta half. So magically the whole thing is exactly delta k times n to the b.
Shouldn't there be a smaller instead of an equal? Because we just put it.
Well, it's O. It's big O, so I mean you're right. Yeah, okay, I should write a subset.
If you change numbers in the exponents, isn't that a problem for O usually?
I didn't change numbers in the exponent. I
We put
added
a bound in.
I added the factor here to that generously.
But I mean, we changed in the bound for the psi I, which is in the exponent. So
Yeah, we made it larger. You're right. So
exactly sure.
it's definitely it's definitely a lesser equal in the usual sense, and in terms of big O, it would be a subset. But the equal is used for this as well, right? Okay, step 3 is essentially dominated by this. We check again all the formulas, so we combine it with step 2. So the total time is these two together, which is dominated by this one. Is also this. And that was exactly the time that we needed for the B delta to contradict the exponential time hypothesis. So this concludes this proof. Now this is a much stronger statement because it includes the size of the formula. So assuming that we find a proper gadget reduction from 3-set to vertex cover, this new result states that there is some constant c, so that vertex cover needs 2 to the c to the k running time, unless this hypothesis is false. But we don't know what this constant is. So it's not showing us how to stop the search for better vertex cover algorithms, but at least there's a certain bound. The proof is similar to the idea we just had. We assume that we have such an algorithm for vertex cover. And it's again a family parametric by this, by the basis of the exponential part. And for a given delta, we again construct an algorithm to solve SAT. So we construct from a given formula the graph and the threshold as sketched before. And this is actually an ordinary polytime reduction. And for the resulting graph, we use our algorithm for vertex cover, where we now set delta to the b. And this b is a constant that comes from the reduction. So the k of the vertex cover, the threshold from the vertex cover problem, was some linear function of the formula size. And we can assume that this is less than some b times n. And we take such a constant b. So this is only given by the specific reduction that we fix, but it doesn't depend on the instance or something like this. It's essentially a measure of the size of these gadgets and so on. So we use our vertex cover algorithm to solve the vertex cover instance and then return yes or no, depending on whether the instance here is satisfiable. So this is a simple algorithm for 3-set. Now let's look at the running time. There's some polynomial part to compute the graph and the threshold. But this is dominated by the time for the algorithm AC, which is just this. And again, I add a polynomial part for the other direction. So any specific algorithm will at least, at most, need an additional polynomial factor. And if we insert, now this k is not the k from 3set, the number of variables, but our k from vertex cover. So we can use this bound here. So again, this is a subset equal. Now this is of the form, the running time, so of the form like we had it in the last theorem. We can, of course, add the k that only makes it worse. If we could do that for every c, we could do that, the b delta for every delta. And that means if we go over all the delta, we can construct such a sub-exponential algorithm, or we can get arbitrarily good algorithms for 3set. But that's a contradiction to this theorem that we've just had. So unless this, okay, the theorem should be true no matter what, but unless the exponential time hypothesis fails, that means there's no such algorithm for vertex cover for all c, so that means there's some c so that it doesn't get any better. This is not completely satisfactory because it doesn't give us the precise constant. It doesn't say 1.3 is best possible or something. And in fact, this seems hard to get. I think there's a bit more that's based on the strong exponential time hypothesis. But for one thing, it's even more technical. For the other thing, this stronger hypothesis is not so clear whether it's really true. For ETH, people are kind of sure that it's unlikely to fail. For the other one, it's not so clear. So this is the best I can offer for vertex cover at this moment. And a result without proof, because it uses a whole sequence of additional steps in between, is the following. Same structure as before, but now we consider the closest string problem. And there, the running time has an additional log up here, or if you pull the log out and combine it with the 2 to the, maybe it would be nicer to let this be DLD. Since we are using arbitrary c's, it doesn't make a difference. So essentially it says that closest string will not have an algorithm that gets below k to the k. Maybe there's a constant in the exponent that can be improved. So it might be k to the k half, which would still be better. We can't exclude that. Not based on ETH, but still the form of the function must be like this. And that means that the algorithm we've seen is not so far from optimal, even though it wasn't extremely tricky. So we've seen a few more techniques how to prove lower bounds. And reduction showing that a problem is W1 hard is nothing else than proving a conditional lower bound, right? We usually didn't write the statements like this. We just stated some problem is W1 hard and then we stopped. But we can always formulate it in this respect. So we should have written unless W1 is FPT, there's no FPT algorithm for this and that problem. And if you unfold all the definitions, these statements are not so different from such statements. So it's a different technique. It also can be formulated in terms of reductions. If you look at the kinds of proofs that we used, we essentially showed towards a contradiction that if we had an algorithm for the new problem, we could find an algorithm for the old problem from of which we don't believe that it existed. And then we turned it around. That's exactly the same that we do with NP reductions. We just don't formulate it as such anymore because we established this notion of reduction. And there is a certain notion of reductions that you can use for these. But they're not as, you need a more relaxed notion of reduction. First of all, to account for the exponential running time part. And then you also need Turing reductions, essentially. In this part where we use this sparsification lemma, we applied here the other algorithm for all of these. So not only once, we didn't construct one instance from one instance, but it was one instance to many different instances. And then we combined the results even. So that's a general Turing reduction that you need here. And therefore, the class of problems that have these kinds of lower bounds are not so nicely structured as in the classical complexity theory. Therefore, it's maybe sufficient to state it like this. So with this last technique on lower bounds, I would like to close the discussion on fixed parameter tractability. And finally come to the next big topic of the lecture. And we'll just cover a few introductory notes, and then next time we'll start at full speed. We'll now talk about randomized algorithms, and maybe also briefly about randomized data structures. And as before, we will briefly discuss computational models to be precise what we mean by this. And with randomization, that's maybe even more needed than for the fixed parameter tractability part. So as before, we based our model on Turing machines. Usually just deterministic ones. And the randomization comes in with an additional input tape. Which is read-only, and we can only move into one direction with the reading head. So in this input tape, initially contains an unbounded infinite sequence of random bits. So strictly speaking, each position is chosen with probability 1 to be 1 or 0, and they're all independent. So these are the maximal assumptions that you can make on a random source. And you might know that this is not always easy to attain. Intuitively, algorithms can use these random bits. And instead of thinking of a tape where these are all pre-computed for you, you can just assume that you have a random bit instruction that each time you call it returns a random 0 or 1. Well, and in algorithms, we often use that in terms of a choice statement. So you have a certain number of choices, and you say randomly choose one of these elements from a set, for example. And of course, you can simulate that by drawing random bits until you have covered all the sets, so by a binary search in the set, in a sense. So what this means is that a randomized algorithm defines a random experiment where even for a fixed input, we have to well, take into account all possible random bit strings that the algorithm uses. If you want to formally model that as probability space, we'll mostly not use that explicitly, but so the states depend on the algorithm. Let's give it a name. And a fixed input x. And this is just a set of all computations. So some run of the Turing machine for which there is a corresponding sequence of bits on the random input tape. Well, and the probability, since all of these sequences are equally likely, we can essentially base the probability by counting the number of different inputs, the number of different fillings of this random input tape that lead to a certain computation. So formally, we would consider the longest, and then we have 2 to the length different 0, 1 sequences, and then we can just count. So it's all considering discrete probability, which makes the math relatively straightforward most of the time. There's one new thing that we didn't have before. And we have a new complexity measure, which is the number of random bits that a machine uses. So sometimes the definition is sometimes a bit different, where you say that the Turing machine may just in every step use a random bit. Our machine might decide not to ask for a random bit each time. So it might run for a long time, but not use many random bits. And as usual, we will define complexity as worst case. So this is input size. So we maximize over all inputs with that size. And random for a specific axis, the maximal number of random bits that we read. And this is still maximized because it might depend on the first random bits, how long we continue. We'll talk about the time measures in a second as well.
Question?
Yes.
But then random of A of n isn't well defined, right?
In what sense is random A of n not well defined?
Because maybe if the number of random choices depends on the random choices, then there is no maximum.
So your concern is that the number of random choices might depend on the number of random choices.
No, on the random choice, the number of random choices can depend on or many random choices.
So maybe a problem is that we might have a machine that keeps on drawing random choices because it keeps on computing. Right? If it runs into an infinite loop, it might, in that infinite loop, use up many, many random bits. And then this maximum formally would just be infinity. But that's the same problem for running time in a sense. We also maximized for running time of all inputs of a certain size, and we also had to live with that possibility.
But if it doesn't run in an infinite loop, but any number is possible, so that there's no maximum. And I don't. I think it's a bit different to this problem for running time.
So it might be that the infinite running time has an infinite small probability in a sense, or a very small probability.
So you have a loop, and each time you toss a coin if you execute
Right.
or not.
So maybe then
Right, that's infinite.
that's
Infinite loop with a maximum number of random choices. It's infinite.
right. So the problem you're hinting at would have been discussed in a second, but maybe we'll just do that before we continue with that and leave a bit of space here. So randomness sounds like a cool idea, but it does give a lot of problems. So a little bit more of notation is the probability for a certain computation. So given an algorithm and given an input and given a certain run of the machine, we can define the computation, right? The probability of the computation. That's easy. Because the given computation reads a certain pattern, and depending on its outcomes, we know what the reads must have had as output. Now comes the interesting part, the probability that A on input X computes a certain outcome. which could be yes, no, or some real output. This is summing over all computations that have this output. Their simple probability. So I mean, this is clearly intended to be the probability of output x. And here the interesting part is that this sum is not necessarily finite. You might have an infinite number of computations with the same output, because you can have such a probabilistic loop as you sketched it. So that's for one thing. Then we can define something like E time, which is the expected time on a certain input. That's again the sum over these probably many computations. Well, and this here, for a given computation is easy, right? Again, that's the length of the computation. And the C by itself can also be of any size. Okay, this is for a specific input, and as usual, the same for n as the max of these. That's boring. For these, we are in principle fine with such a loop that repeats only, say, for once. So something like while random bit is 1, we do something, because the expected time then would actually still be constant even. Or in the general case, you can often have such constructions where the expected time is still well defined, even though the possibility of infinite runs is there, but it has an exponentially decaying probability. So does that help you a bit? So that's for one thing.
That's clear, but the problem was with the...
Right, okay. Yeah, we'll come back to that. Oh, maybe next time. So let me just add that these are usually well defined, even if infinite runs are possible. The prototypical example would be something like this. The problem is that expected times are much harder to determine than worst case times. So we really would like to work with worst case times. And at least in complexity theory, we would like to do that. And so I'll give the time definitions, and then we'll finish for today. And we have something to discuss. So the time of a randomized algorithm A on a specific input is here again taken as the maximum. Even for a specific input, it's the maximum of all computations. And this must be set to infinity if such an infinite run is possible, right? Just to write that down. Of course, we maximize again if we use n instead of a specific input. We maximize over all these for this inputs of that size. That's as always. So I guess the answer to your question is that, so your question would be rephrased in terms of this time definition. What if this max is not well defined? And the point is either the set of computations on this input is finite or it's infinite.
Yeah, with this definition, it's okay.
Right.
But we need the infinity as a case in the operator definition too.
So let's get back to that now. So here this can also be infinite if there is some run. So maybe maybe it would be better to write that maximum
for both.
More explicitly. So that's the random bits used by C, where C is a computation of A on X. And we understand that max here means if this set is infinite, if there's infinitely many computations. Okay, we have the problem that there might be infinitely many computations and they still don't use infinitely many random bits. But either there is a maximal number that they all use, or it's unbounded and then we set it to infinity again. We don't have anything like a supremum that's only approached infinitely close but never attained because we're in the discrete real natural numbers, right? Yeah. Okay. So all of these maxima can be infinity, if the algorithm has such infinite loops or infinite loops with exponentially small probability. Right.